Okay, in this lesson I'm going to look at what we call mutually exclusive events. And we say that events A and B are mutually exclusive if and only if the probability of A intersection B is 0. So what does that mean? Well, they cannot both happen together. They cannot both happen together. So let's have a look at an example here. It says a set contains the integers from 1 to 30. An integer is selected at random from the set. I define two events. Event T is the number selected as a multiple of 3. Event F is the number selected as a multiple of 5. I want to draw a contingency table and investigate whether or not T and F are mutually exclusive events. So let's have a look. Contingency table, a few vertical lines, a few horizontal lines. T and F are my events. This has to be T complement. This must be F complement. Capital sigma, capital sigma. T represents that the number selected from the numbers 1 to 30. T represents the event that number I select is a multiple of 3. So T complement will be the number I select is not a multiple of 3. F is the number I select as a multiple of 5. So F complement would be the number I select as not a multiple of 5. So I'm going to fill in my contingency table. First thing, numbers from 1 to 30, integers from 1 to 30. We've got 30 possible outcomes here. And I'm going to look at all the multiples of 3. How many multiples of 3 are there? Well, there's 3, 6, 9, 12, 15, 18, 21, 24, 27, and 30. Okay, and that's 10. There's going to be 10 multiples of 3. Which means there's 20 numbers in there that are not multiples of 3. And if I look at the multiples of 5, 5, 10, 15, 20, 25, and 30. There's 1, 2, 3, 4, 5, 6. There are 6 multiples of 5 in the integers from 1 to 30. So there are 24 numbers that are not multiples of 5. What does this cell represent? Well, this cell represents the numbers that are multiples of 3 and multiples of 5. So what numbers are multiples of 3 and 5 here? Well, 15 is a multiple of both, and so is 30. So there are actually two multiples in there that are multiples of 3 and multiples of 5, which means there must be 4 multiples of 5 that are not multiples of 3, and there must be 8 multiples of 3 that are not multiples of 5, and there must be 16 numbers from 1 to 30 that are neither multiples of 3 nor multiples of 5. I won't list them all out. It's too time consuming, but I want to investigate whether or not these are mutually exclusive events. And to do that, I just have to think about this. Can a number be both a multiple of 3 and a multiple of 5? If it can, then they are not mutually exclusive. So I'm going to say T and F are not mutually exclusive. And I'm going to give a reason. Since the probability of, in fact, let me write it down a bit lower, since the probability of T intersection F is equal to what? Well, it's 2 out of 30. And that is not equal to 0. Remember, they're only mutually exclusive if there's no chance of both events happening at the same time. So in this case, there's a 1 in 15 chance or a 2 in 30 chance that both events will happen at the same time, so they are not mutually exclusive. Okay, so investigate mutual exclusivity, we figure out whether they can happen together. Here's another example. It says A and B are mutually exclusive. So here we're given that they're mutually exclusive events such that the probability of A is 0.6 and the probability of B is 0.2. I want to evaluate the probability of A or B. Now I could do this using the addition rule, or I can do it, I'm going to actually just draw out a contingency table. My events here are A, and A complement obviously, and B complement. And we know the sum of all the probabilities for any experiment is 1. So the first thing I'm told is that A and B are mutually exclusive. And A and B we know are mutually exclusive if and only if the probability of their intersection is equal to 0. So that has to be 0. The other information here, the probability of A is 0.6. Well, all the probabilities for event A is 0.6. The probability of B is 0.2. And I'm ready to fill in everything else. That's a 0, so that has to be 0.6. This has to be 0.2. These two together have to add to 1. That must be 0.4. This has to be 0.8. Which means this one has to be 0.2. To find the probability of A union B, or A, notice A union B and A or B means the same thing. The probability of A or B complement here is equal to this cell, 0.2. So, the probability of A or B has to be equal to, well, they're complementary events, so together they have to add up to 1. It has to be equal to 0.8. The other way to use this is note the addition rule. The addition rule says the probability of A or B happening is the probability of A plus the probability of B minus the probability of A and B. The probability of A here is given as 0.6. The probability of B here is given as 0.2. The probability of A and B, where we're told they're mutually exclusive events, so the probability of them happening together is 0. So you can work out that's 0.8. That's the probability of A or B. So you can use a contingency table and figure it out from there. Identify that cell as the complement of the union and then work out what the union is. Or you can just use your addition rule for probability, remembering that if they're mutually exclusive, then they have a probability of 0. Okay, so practice those questions, get used to mutually exclusive events. We should be able to complete section 5.5 at this stage. Okay, so practice, practice, practice.